In this lesson, we are going to continue our study of polar curves. We will start by graphing some more polar curves, and then we are going to generalize some of our ideas from calculus to these curves. We'll be able to find slopes of tangent lines and things like that. So first, let's sketch the graph of the polar equation. R is 3 sine of 3 theta. This will produce a rose-shaped curve with like some little petals. So the first thing we have to do is graph R as a function of theta in Cartesian coordinates. And to do that, we need to find the period of this sine function. So set 3 theta equal to 2 pi. So that tells you that theta is going to be 2 pi thirds. So by the time you've gone through 2 pi thirds, you've gone through one cycle. So one cycle by 2 pi thirds, one cycle by 4 pi thirds, and by 2 pi we'll have gone through 3 complete cycles. This number in there with the theta tells you how many cycles you've gone through. Halfway is pi thirds, 3 pi thirds or pi, 5 pi thirds. And then from there, things are further divided into 6. So there's pi 6. 1/6 more than pi thirds is actually pi halves. Between 2 pi thirds and pi, that halfway point is 5 pi 6. 7 pi 6, 6 pi 6, 7 pi 6, 8 pi 6, 9 over 6 would be the same thing as 3 pi halves, and here we'd have 11 pi over 6. It's just all the angles on the unit circle listed out, not a problem. All right, and this curve is 3 sine theta, so an amplitude of 3, and sine begins at the origin. By pi 6 we're up at 3, pi thirds we're at 0, pi halves were at -3, 2 pi thirds were down to 0 again. And then the cycle repeats. 5 pi 6 we're at 3, pi we're at 0, 7 pi 6 we're at -3, 4 pi thirds we're back at 0. Boom. Up, down, down, up. Okay. All right. Now this curve, and this is the theta axis, this is the r axis. So we start with a radius of 0 at the angle of 0, so we're actually beginning at the pole. By pi 6, we're up at 3. So this is pi 6, 1, 2, 3. And as the angles are increasing to pi 6, the radii are increasing to 3, so this is going to sweep out. And as we approach pi thirds, we'll start a little bit. As we approach pi thirds, the radius goes back down to 0. There you go, like that. Now, between pi thirds, and that is, so we did this part. Next, we're going to do this part. So the easiest point to do is pi halves. When you have an angle of pi halves, your radius is -3. So that point is going to be here. And all of these points on the first bit, they have negative radii as well, so they reflect down like that. And then all of these points here reflect over there. So there's your next loopy. And those little dots that I drew, I'm going to erase them because they were just to be reflected. They're not actually part of the graph. All right, and then the last bit, from 2 pi thirds to 5 pi 6, by 5 pi 6, we are up at 3, so that's up here. And you were at the origin, and then your angle increased, and your radii also increased. And then by pi, we're back down to 0. And we should check and see what happens as we keep going, but it's going to actually end up that we're going to hit the curve again. So from pi to 4 pi thirds, we can think about this point that is -3, 7 pi 6. So here is the point where we have +3, 7 pi 6. That's going to reflect over here. So all these points that were here, those are all going to go here. And all these points that are over here, well, they're going to reflect onto this. So it turns out that for this particular curve, it's only necessary to graph up until pi. All right, next we have 1 plus 3 cosine of theta. So in this particular example, we're sort of lucky because we don't have any kind of funky period going on. The period is just 2 pi. So let's start by graphing 3 cosine of theta. It's a plain old cosine curve, except for it has an amplitude of 3. So it goes through one cycle in 2 pi, and has a maximum value of 3 and a minimum value of -3. So it begins at 3, by pi halves we're down at 0, by pi we're at -3, 3 pi halves we're at 0, and by 2 pi we're back up at 3. So there's the unshifted cosine curve. Now take that curve and shift it up 1. So we're up at 4, pi halves we're at 1, pi we're at -2, 3 pi halves we're at 1, and 2 pi we're back up at 4. Okay, so this curve begins at the angle of a radius of 4, angle of 0. So way the heck out here. By pi halves, radius of 1. So as the angles decrease, as the angles increase to pi halves, the radii decreased. And for a little bit, you're positive until by pi, you're actually have a point -2 pi. So that's going to be this point. So we're positive for a little bit, but then we actually follow in this direction. And so all these points here got reflected onto those. All these next points here reflect over onto this. By 3 pi halves, we're back at 1. And by 2 pi, we've gone all the way around back to 4. And you have to just think about these rays, that those rays are getting shorter, and that means that the radius is decreasing. The trickiest part are these negative parts that reflect. Those are by far the hardest bits. All right, now everything we've had so far has either had an adjusted amplitude or an adjusted period, and this one has both, so stuff's going to look a little bit different here. So first, let's graph a Cartesian coordinate, or this curve in Cartesian coordinates. And we'll start by graphing 2 cosine of 2 theta. And so if we set 2 theta equal to 2 pi, we find that theta is pi. That's how long it takes this to go through one cycle. By 2 pi, we're through 2 cycles. So halfway to pi halves is pi quarters, 3 pi quarters, 3 pi over 2, 5 pi quarters, and 7 pi quarters. And if we're at least initially just graphing r is 2 cosine of 2 theta, we're going to start off at 2. By pi quarters we're at 0, by pi halves we're at -1, 3 pi quarters we're at 0, and pi you're back up at 2. Back to 0, down to -2, up to 0, up to +2. Now we're going to take this curve and we're going to shift it up by 1. Okay, so we start off with a radius of 3 at the angle of 0. So 1, 2, 3. By pi over 4, our radius has decreased to 1. So the radii have gone down. And at some point in time, which looks like it must be probably as close to pi thirds, radius has gone down to 0. Now the question is, what happens to, one of the questions is, what happens to this little bit? Well, at an angle of pi halves, your radius is -1, so this point is reflected down, and all those little bits there, they get reflected over here. So you've started that way and that way. And then that will just reverse and undo, and we'll go back up to the origin. So that's this little part. And from there, let's just continue in purple. So from that point on, by 3 pi quarters, we're at a radius of 1 again. By pi, we're back at that radius of 3. Okay, and then by 5 pi quarters, we're back to a radius of 1. And somewhere down there, we're going to go to 0. So, to 0. And now the next bit we have is this part. We have the coordinates -1, 3 pi halves, so this point gets reflected up to there, and all these little dots reflect onto those little dots, goes back down, so that's this part, and by 2 pi we've gone back up to being 3. Looks a little bit like a bow tie. Bow ties are cool. Alright, so now that we've sort of exhausted most of the typical examples for graphing curves, let's talk about how might we do some calculus with these polar curves. So we have functions that are parameterized by r equals a function of theta. So the thing to remember is that r is actually a function, not just a variable. And the relationship to the Cartesian coordinates is that x is r cosine theta and y is r sine theta. So we actually use the derivative formula we have for parameterizations to find the derivative of this, the derivative slope of tangent line to this curve at any given point. So the derivative of y with respect to x is given by dy d theta over dx d theta. Same formula as before, it's just we have thetas instead of t's. And now what you do is you take this y parameterization and you differentiate it, and you have to use the product rule because r is a function. So differentiate r first. This will be dr d theta times sine theta, plus leave the r alone, multiply by sine's derivative, which is cosine of theta. Similarly, to find dx d theta, that's going to be dr d theta cosine theta, this time minus r sine theta, because of the fact that cosine's derivative is negative sine. It is probably far better to remember how you get this formula, that is by taking the derivative of the parameterization, as opposed to just trying to memorize it blindly. Personally, I have to write down x equals r cosine theta, y equals r sine theta every single time, and then just do derivatives using this formula. And for each situation, the function r equals f of theta will be different. So, for example, in the previous example, we had r equals 1 plus 2 cosine of 2 theta. So to find the slope of the tangent line, you'd have to insert this r wherever there's an r, and insert its derivative wherever there's a dr d theta. And the reason the sine and cosine are there is because that's the relationship between these two systems, involves using that sine and cosine. So let's use this formula to find the slope of the tangent line to r is cosine theta over 3. So I just remember that x is r cosine of theta, y is r sine theta. And look, I have to rederive the formula because I already forgot it. dy dx is dy d theta over dx d theta. Well, dy d theta will be d r d theta sine theta plus r cosine of theta over dr d theta cosine theta minus r sine theta. And now input everything. So notice first of all that dr d theta is the derivative of cosine of theta over 3. Well, the derivative of cosine of stuff is negative sine of that stuff multiplied by the derivative of theta over 3, which is 1/3. So we'll have negative 1/3 sine of theta over 3 times sine of theta plus r, which is cosine theta over 3 times cosine theta. All this over negative 1/3 sine of theta over 3 cosine theta minus cosine theta over 3 times sine of theta. Now, at theta equals pi, the slope will equal negative 1/3 sine of pi thirds times sine of pi plus cosine of pi thirds cosine of pi all over negative 1/3 sine of pi thirds cosine pi minus cosine of pi thirds sine of pi. So we have negative 1/3. Sine of pi thirds is root 3 over 2. Sine of pi is 0. Plus cosine of pi thirds, which is 1/2, times cosine of pi, which is negative 1, all over negative 1/3 times root 3 over 2 for sine of pi thirds again, times negative 1, minus 1/2 times 0. So this gives us negative 1/2 over positive root 3 over 6, which is the same thing as negative 1/2 times 6 over root 3, or negative 3 over root 3, which if you rationalize or simplify comes out to negative root 3. So the trickiest thing here is that things can get a little bit tedious, and you have to understand that this thing that I just put a box around right now, that's actually just not your answer, because you're asking about what is the slope of the tangent line in the xy plane. You have to consider how you'd take that curve and make it back into the Cartesian system. All the calculus you know is for that Cartesian system. So just be aware of that. It is not as easy as just take the derivative of that thing and plug in pi. All right, let's find the slope of the tangent line to r is 1 over theta when theta is pi. So once again, we have x is r cosine theta, y is r sine theta, and to find dy dx, we find dy d theta over dx d theta, and dy d theta is dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. And since we have r is 1 over theta, or theta to the negative first power, we have that dr d theta is negative 1 theta to the negative 2. So inputting all that we know, we have that our derivative here is negative 1 over theta squared times sine of theta plus 1 over theta times cosine of theta, all over negative 1 over theta squared cosine theta, minus 1 over theta sine theta. And at the specific value of theta is equal to pi, input that, and we have dy dx, or the slope of the tangent line, will be negative 1 over pi squared sine of pi plus 1 over pi cosine of pi divided by negative 1 over pi squared cosine pi minus 1 over pi sine pi. So that first term will be 0. The second term will be negative 1 over pi, since cosine of pi is negative 1. In the denominator, we'll have positive 1 over pi squared, because cosine pi is negative 1, and then plus 0. So we have negative 1 over pi multiplied by pi squared over 1 gives us negative pi for the slope of this tangent line. And we haven't done it in this example, but if you wanted to find the equation of the tangent line, you're going to have to take this value of theta and plug it into these equations. So for example, in this equation, we know that x is r cosine of theta. So x is 1 over theta cosine of theta. And if theta is equal to pi, the x coordinate is 1 over pi cosine of pi, which is negative 1 over pi. And the y, which is r sine of theta, since r is 1 over theta, our y is 1 over theta sine theta. If theta is equal to pi, the y is 1 over pi sine pi, which is 0. So the point in this context is the point 1 over pi, 0. If you had to find an equation of a tangent line, you're going to need to use that. All right, let's graph the curve for cosine of theta, and we'll find all the points where the tangent is horizontal or vertical. And then we're going to find a Cartesian equation for the curve, and we're going to verify that the analysis is probably correct. So first of all, sketching for cosine theta. This is actually a 1 petal rose. Pi halves, 3 pi halves. So we'll begin at 4. By pi halves, we're at 0. By pi, we're at negative 4. By 3 pi halves, we're back at 0. And by 2 pi, we're back at 4. So it looks like we start right here. And by pi halves, we're already back at 0. So what's going to happen here is that the radii decrease as the angle increases. And then this portion here is a bit tricky, but that point right there, that's negative 4 pi, that's this point, which reflects back to here. So it actually turns out that all of these points over here are reflecting down to there. This bit's reflecting there, middle bit's reflecting there, this last bit's reflecting there. And if you continue past pi, you're just going to trace the circle one more time. So this is actually a circle of radius 2 with center at 2, 0, and we'll prove that in just a moment. So we're going to find where the tangent is horizontal or vertical. So what you have to first find is the derivative. dy dx will be dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. And in this context, dr d theta is negative 4 sine of theta. So let's input that. So you have negative 4 sine theta times sine theta plus r, which is 4 cosine theta times cosine theta. All that over negative 4 sine theta times cosine theta minus 4 cosine theta sine theta. So that gives us 4 cosine squared theta minus 4 sine squared theta over negative 8 sine theta cosine theta, which is the same thing as cosine squared theta minus sine squared theta over negative 2 sine theta cosine theta. So we will have horizontal tangents if cosine squared theta minus sine squared theta is equal to 0. That is the same thing as saying cosine squared theta equals sine squared theta, or as saying cosine theta equals positive or negative sine theta. And cosine of theta will equal sine theta at things like theta's pi quarters, 5 pi quarters, etc. Another way to say that is theta is pi quarters plus n pi. And cosine of theta will be negative sine theta, as in sine and cosine are opposites, at angles like 3 pi quarters and 7 pi quarters. So theta is 3 pi quarters plus n pi. And so now let's move on to the vertical tangents. We'll have vertical tangents if negative 2 sine theta cosine theta is equal to 0. Whoops. And that will occur if either sine theta is 0 or cosine theta is 0. And sine of theta is 0 at all of the integer multiples of pi, so theta is pi times n, where n is an integer. Cosine theta is 0 at all the pi halves, so pi halves plus n pi. Another way to express those as 1 would be theta is pi over 2n. That gets all of the half pies, like 1/2 pi and 3/2 pi, but also gets all of the whole pies, because when you say input n equals 2, notice that you get pi. Similarly speaking, these could be expressed as theta is pi quarters plus n pi over 2. It's only 1/2 pi from pi quarters to 3 pi quarters. And now we're just going to verify that this actually is a circle like we thought. So for that, remember that the equation we had was r equals 4 cosine of theta. And since we know that x is r cosine of theta, we know cosine of theta is x over r. So we have r equals 4 times x over r, or r squared equals 4x. R squared is x squared plus y squared. We move the 4x over. And we complete the square by adding 4. So x minus 2 squared plus y squared equals 4. It's a circle with center to 0 and radius equal to 2, which is what the picture we had sort of showed us. All right, now we're going to graph the curve r is 1 plus cosine of theta, and we're going to find the points on the given curve where the tangent is either horizontal or vertical. a normal cosine curve would have begun at 1, been 0 at pi halves, been -1 at pi, back to 0 at 3 pi halves, and back up to 1 by 2 pi. But we don't have a normal cosine curve, we have a cosine curve shifted up 1, so we begin at 2. By pi halves we're at 1. By pi we're at 0, by 3 pi halves we're at 1, and by 2 pi we're back up at 2. So this curve begins at an angle of 0 and a radius of 2. By pi halves we're down to 1. By pi your radius has shrunk to nothing. By 3 pi halves it's increased from nothing to 1. And from 3 pi halves on to 2 pi, your radii goes back up to 2. All right, now to find whether the tangent is horizontal or vertical, we find the derivative. So dy dx is dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. And dr d theta here will equal negative sine of theta. So we have negative sine of theta times sine of theta plus r, which is 1 plus cosine of theta times cosine of theta over negative sine theta times cosine of theta minus quantity 1 plus cosine of theta times sine of theta. And that simplifies a little bit to negative sine squared theta plus cosine theta plus cosine squared theta over negative sine theta cosine theta minus sine theta minus cosine theta sine theta. Now the denominator is simple enough to simplify. That's the same thing as negative 2 sine theta cosine theta minus sine theta. The numerator, we're going to have to factor this, and to do that you're actually going to have to convert these sine squared thetas into cosine squared thetas. And you do that by observing that negative sine squared theta is 1 minus cosine squared theta. And finally, when all is said and done and all like terms are combined, we have cosine squared theta, 2 of them in the numerator, plus a singular cosine of theta minus 1. In the denominator, I can take out the greatest common factor of negative sine of theta. So we have negative sine of theta times 2 cosine of theta minus 1. Oh, plus 1 since I took the negative out. Whoopsies. Okay. Now to factor that numerator, you say, well, we got 2 cosine of theta here, singular cosine of theta there. To make negative 1, I have to have 1 negative 1 and 1 positive 1. And a little guessing and checking tells you the negative 1 is there, the positive 1 is there. Whew, these take a long time. All right, so now let's figure out where is this going to be horizontal. So it'll be horizontal if 2 cosine theta minus 1 is 0 or cosine theta plus 1 is 0. So that's the same thing as saying cosine theta is a half, and that occurs when theta is pi thirds and 5 pi thirds. Next one is when cosine theta is negative 1. Well, that's true if theta is equal to pi. Will be vertical if either negative sine theta is 0 or 2 cosine theta plus 1 is 0. And so sine of theta is 0 at theta equal to 0, pi, and 2 pi. And this is the same thing as saying cosine theta is negative a half. That occurs for theta equal to 2 pi thirds and 4 pi thirds. Now the one tricky thing here, I'm putting boxes around what's okay and no boxes around what's not. Theta equals pi is a problem because at theta equals pi, we're saying we have a horizontal and vertical tangent. Which one is it? You can use your picture to make a guess. So let's pull that picture down. At theta equals pi, which is this point right here, it appears to me at least that that tangent looks like it's going to be more of a horizontal thing than a vertical thing, but the question is, how do you prove that? So what you're going to have to do is take this expression and find the limit as theta goes to pi from either the left or the right, and that will tell you whether or not you have a vertical or horizontal tangent. If that limit is 0, it's a horizontal tangent. If that limit is infinite, it's going to be a vertical tangent. So we're going to find the limit as theta goes to pi, we'll just say from the left of the derivative. And that derivative was 2 cosine theta, minus 1, cosine theta plus 1 over negative sine theta times 2 cosine theta plus 1. And the clever thing that you can do is observe the parts that are sort of problematic and giving you the 0 over 0. That's this portion and this portion. So I'm going to flip-flop the order of these things, like this. I'm going to think about this as 2 cosine theta minus 1 over 2 cosine theta plus 1 times cosine theta minus 1 plus 1 over negative sine of theta. And this doesn't work for derivatives, but for limits it's okay. You can limit each portion separately as long as the limits exist. So for the first ratio we have there, when you input theta is pi, you don't have any division by 0 or funny business going on. All that we have when you've input theta equals pi is your numerator ends up being negative 3, and your denominator ends up being negative 1. So that part we're just going to write as negative 3 over negative 1. And now we have the limit as theta goes to pi from the left, cosine theta plus 1 over negative sine theta. This is a 0 over 0 limit, so use L'Hopital's rule. And the derivative of cosine is negative sine. The derivative of sine is cosine, so negative cosine. Now we input pi and we get 3 times negative 0 over negative 1, which is 0. So that means at theta equals pi, the tangent is horizontal.